Sree Ranjani. Uh, it's morning time for you, early morning, I think.
Oh, it's 9 a.m. It's totally
Oh,
fine.
oh, okay, yeah, then it's fine. Yeah, um, to- so we will have our next session, which is session 8 of this FDP on uh, secure and intelligent SoCs, system on chips. So today we have with us Dr. Sree Rajendran. Uh, I'll first introduce her. Dr. Sree is an assistant professor in the Department of Electrical Engineering and Computer Science at Florida Atlantic University in Boca Raton, Florida. Her research focuses on hardware security, secure system on chip design, and IoT security, with particular emphasis on hardware Trojan detection, logic locking, and hardware verification for trustworthy embedded systems. Dr. Rajendran is a senior member of IEEE and has authored numerous research articles and book chapters in VLSI design, hardware security, and secure IoT architectures, along with serving as an active reviewer and contributor in leading international conferences and journals. It's a pleasure for us to have you here to share your insights into this very important area to our participants. I'll hand over to you and let's start. Thank you.
Thank you, Dr. Malish, for introducing me. Hello, everyone. Good evening to you all, and good morning to some of you, I believe. Thanks for having me here. Today, we are going to discuss about securing SoCs against the hardware vulnerabilities. And myself, Dr. Sree Rajendran. I'm from FAU, Department of Electrical Engineering and Computer Science. So, before going into the talk, I like to express my sincere gratitude to FAU in providing me approval in giving a talk in this particular topic. And I want to grateful to the organizers of this faculty development program in the title of Secure and Intelligent System on Chips, which is Need for an Hour. And I like to thank CUSAT University for giving the opportunity for the participants and the speakers like us in order to share our knowledge and develop a community gathering over there. Thank you all. I thank the participants also. So the outline of this presentation today is we are going to discuss about a high-level overview on the security vulnerabilities, particularly at the hardware side, in with respect to that of an SoC design, that is a system on chip. So let us have a quick overview of what is an SoC, system on chip. Obviously, many speakers would have covered the previous sections, but I like to take some bit of time in expressing what is an system on chip and what its characteristics with respect to that of an hardware design. Then we have major applications of SoC where we are using this SoC right nowadays, where we are in the real world systems where we are right now. And we are going to touch up with an hardware threats and vulnerabilities, which is going to be the essence of this particular FTP session. And then we discuss about the countermeasures and let us wind up with the different summary of all the topics what we have covered in this section particularly. You can stop me anytime and I will be happy to answer your questions over there. So, reality with electronic systems and devices, where we are right now, where we are using these applications of the SoC. Right now, obviously, everyone in our day to day life, electronic systems and devices and the gadgets are the part of our day to day life. And we are not only with bounded within one electronic devices or a gadgets, obviously, we will be having a multiple electronic systems and gadgets throughout around us. For example, right now in this table, I have two mobile phones and two iPads and one laptop and one screener. Don't judge me that I have two mobile phones and two. It's not a show off. I'm just telling you this is the right place to tell how much we are bounded to that of an electronic systems over there. However, I got one more mobile phone and tablet for my daughter in this Black Friday deal. That's a good deal. Then this is the right now we are. So we will have multiple gadgets. We'll be using multiple electronic systems in our day-to-day life. Not only the gadgets, how about the appliances? We have n number of appliances which are automated, from washing machine, microwave, dishwasher, and everything. Coffee machines are automated nowadays. So whenever I wake up at the 6 o'clock, my coffee is ready in my coffee machine. It is programmed like that. And home automations and car automations, everywhere we have some type of an electronic systems and devices. And what is the controlling point over there? These electronic devices are controlled or by that of an electronic ICs, that is nothing but an SoCs. So this is the data I have in 2026. We are almost in 2026 right now. So the consumer electronics to become $1 trillion industry with respect to the top and electronic systems. So the revenue in the consumer electronics market, the growth from 2024 to the top and 2029, that is the prediction with respect to the top is nothing but a billions of dollars. So you can see the growth from 2024, that is the previous year, to that of next 5 years in 2029, we will be having a millions and billions of US dollars are invested in this consumer electronic market. So what we are dealing with, we are dealing with n number of electronic systems and gadgets throughout our daily life. From the alarm clock, we are switching off in the night to the top an alarm clock switching on in the night. We are bounded with the top n number of electronic systems and gadgets over there. So where we are right now, we are right now with that of an driverless car, that is self-driven car, and we are with an Internet of Things. Now Internet of Things is renamed as an Internet of Everything. So everything we are connected with it of an one roof. We call them as a cloud computing. We call them as an internet over there. So we need all these gadgets and appliances are connected into the of an one roof over there. That's what we are bounded to. So right now I'm like 1,000 to 2,000 miles apart, but I'm connected to you all guys. We are like an how many participants? We have 75 participants which are connected at of one internet source over there. So this is what we are in reality over there. Where will be in the future? That is the nightmare over there. Where will be in the future? Our future is going to be like this. Everything is an virtual going to be. Everything is an automated. Everything is going to be connected. We are going to communicate with a large number of devices without connecting to them. So this is what the reality right now. We have an headset computers, we have an AV glasses, we have a health bracelets which are monitoring our health system, which is required most recently. We have a clips on sensors. Everywhere we have a sensor. What is my heartbeat? What is my body temperature? What is my room temperature? How my room temperature and body temperature are correlating? Am I okay with that or not? And we have a smart watch to monitor our each and every seconds of our life. So this is where the future will be. So knowingly or unknowingly, we are using all the electronic devices or the systems throughout our life, and we are bounded to that. And believe me, these electronic systems and devices are looking forward. They make our life easy. Yes, the smartwatches always monitor our blood pressure. The health bracelet always counts our steps over there. It monitors our blood glucose level. Everything is totally fine. But when it comes into the privacy and security, that's what I'm going to touch on this class. So the big picture with respect to the top of electronics and digital systems, I have seen some of the topics with an ISA model, risk ISA model. Yes, this is the big picture what we are dealing with and digital systems or electronic systems. So at the application layer, we have a compiler and we have some risk assembly at the assembler, which converts the program into the top of an assembly language model, that is a high level language. Then the machine code, there will be having a loader and linker. It will be converting the high level language assembly language into the of a machine code of binary values, and the instruction set architecture, which is the bridge to communicate with that of an hardware level and the software level. And you will be communicating with the hardware, which is nothing but your central processing unit. The central processing unit is built with of a circuits like an encoder, decoder, ALU, multiplexer, demultiplexer, and some input output ports, some memory units over there. So how you are going to build all these modules, all these sub modules, and modules are built using the logic gates. So when it comes into the top an IC chips, you have to model these logic gates at the transistor level, RTL level, register transistor logic. So these transistors, that is a CMOS structure, what we are using is built with the help of the silicon. So from the top to bottom approach, we are dealing with the software at the compiler level, but we are working at the top and hardware level, that is at the silicon level. So in today's session, we are going to deep dive into the top and security vulnerabilities with respect to the top and silicon level or the transistor level, which is the hardware and which is the heart of any computational system or any digital system. And these components, the hardware components or the modules or the architecture, what you have discussed in the previous session, I believe. And these architectures are built with the help of an SoC, that is nothing but your IC chip, system on chip. So the entire architecture or built with the help of an IC chip, that is nothing but a system on chip. That's what we are going to cover up. So if your system on chip is vulnerable to any type of an hardware attack or hardware threat, definitely the entire computational system is going to be a vulnerable. It might be the software attack, it might be the hardware attack, or it might be the hardware software code design attack. Nowadays the hot topic is an hardware software code design. So both the all type of attacks are possible, all types of vulnerabilities are possible if your SoC, system on chip, is vulnerable to certain type of an hardware threats or vulnerabilities. That is what we are going to discuss in today's session. So just to have an high level overview, what is an IC chip? Since SoC itself is an IC chip. So the IC chip is nothing but an integrated circuit. We call them as an IC in short form, is a part of larger body of knowledge known as an electronics engineering. So why we are going to give high importance to this IC chip? Since this is going to be the brain of the system, this is going to be the heart of the system. It is going to be the controlling the entire electronic systems or any type of a gadgets. So this IC chips plays a major role over there, and they are the subfield of electronics engineering encompassing the particular logic and circuit design techniques required to design integrated circuits. So IC consists of a miniature electronic components built into electrical network on a monolithic semiconductor substrate by process called a photolithography. So we have a 9 major steps in IC design flow. We are not going to touch up all those things, but you should know the IC design process and the IC SoC design process are going to be the same. So what are the type of ICs we have? We have a digital ICs, we have an analog ICs, we have a mixed signal ICs, we have a three-dimensional ICs, and we have a system on chip also. So each ICs are used for a preferred applications. That's why we call this an application specific ICs. The digital ICs are characterized as a logic ICs such as a microprocessor and microcontrollers, and they are the programmable devices, and they have a power management ICs in that, and they are going to control the entire system over there. So they are going to module each and every instruction step by step over there. So the controlling part is going to be the digital IC. However, the analog ICs or a linear integrated circuits and RF circuits, they are used for a communication purposes. However, the mixed signal ICs, they have the both characterized as a data acquisitions ICs, that is having an A to D converter. We need an analog to digital converter. We need a digital to analog converters. And these ICs, mixed signal integrated circuits, are used for the entire communication purpose over there. So we are using sensors. What is the sensors? The sensors, the input will be the analog form. However, the processing will be in the digital form. So we need a to D converter over there. And once the processing is done, the computation is done, the output will be in the digital form. But as a human, we need to know in an analog format. Either it might be the voice message or it might be the video over there. So we need a D to A converter over there. So these mixed signal integrated circuits are used. And we do have a three-dimensional integrated circuits also when you are combining digital ICs, analog ICs, and mixed signal ICs over there. However, these type of ICs are now integrated into that of a single chip, that is nothing but your system on chip. So what is common in any type of an electronic or digital systems? There are n number of components when you break out any type of an digital systems. You might see the green color PCB board with that of an integrated along with that of an capacitor, resistors, inductor. But what is the major important part is nothing but your IC chip. in your any digital systems, if you reverse engineer or break down the system, you might see when either rectangular or square type of an IC black color module in your digital systems. So those are nothing but the heart, the controlling part of your gadgets or systems. They are nothing but then ICs, integrated circuits. The integrated circuit, it might be the application specific IC, or it might be then FPGA, or it might be a SoC also. So any type of an IC in common is going to play the major role in controlling the entire digital systems. So if your car is automated, if your home is automated, what is the controlling part? The IC is the controlling part, and that IC is nothing but your SoC right now. So we have to check what is the era in the IC. So the first semiconductor chip held has a two transistor. What is inside the IC? It is nothing but the transistor. We are dealing with the CMOS transistors over there. So the first integrated circuits held only few devices. It may have a resistor, transistors, capacitors, and diodes over there. And we can see the size of the computer. The first manual computer is larger than the room size. That's what we always say. But right now we have the miniature devices with n number of computations, can be used for n number of applications. And IBM has released the smallest computer chip that is nothing but your lesser than the nail size, thumbnail size over there. So where we are that revolution happening, we started with a small scale integration with the 7400 series of ICs with 10 to 100 transistors built in, integrated into that. That's what we have used in our laboratories over there. And we have a medium scale devices or medium scale ICs with a countable of transistors from 100 to 1000 transistors. And then we move to large scale integrated circuits where the count of transistor is from 1000 to 10,000 transistors. Then we are right now with an VLSI, very large scale integrations, where you are integrating more than 10,000 transistors in your IC chip. And then we have an ultra large scale integrations also, and some disagreement, and we will be touch up over there. So this is the era or evolution in IC design. So SoC will fall under a VLSI over there. So very large scale integration. So how it is possible? Either we can just we can see the transition from the room size computer to the top and miniature devices by increasing their applications, by reducing the power consumption, by increasing the durability, longevity of the devices. So how this is possible? How this is achieved? This is possible only with the technology. The technology advances over there. The today's chip can contain 100 million transistors. Okay, we can say it is more than 100 million. That's a 1 billion transistors are also possible. The transistor gate lengths are now terms into the nanometer. We call them as a technology term. It's a transistor scaling, which is the basic block for this technological advancement over there. Right now, anyone in the VLSI design or SoC chip design will be aware of this Moore's law. Dr. Moore have predicted at approximately at every 18 months the number of transistor on a chips doubles. So I always crack a joke in my class, will the transistor will produce another transistor, or it will, how this multiplication is happening? The multiplication or the increase in the number of transistor is happening through this technology advancement. We are reducing the transistor sizes by means of transistor scaling without compromising on its performance, and we are always working on the minimum power consumption with the minimum area and the maximum speed and maximum longevity over there. So the consequences, what we are using, what we are facing with this technological advancement is nothing but the components connected on the printed circuit board now can be integrated into the top and single chip. That is how we have advanced or evolved from the top and room size computer to the top and miniature devices, what we are using in our day-to-day life. That is nothing but your SoC system on chip. Okay. So with that, we are understanding what is an IC and what is a system on chip. So IC, it's nothing but an application specific integrated circuit. It performs a specific function. It might be the encoder, it might be the decoder, it might be the AND function, it might be the NOT function, it might be the multiplexer, whatever it may be for a specific function. And it contains a single processor, requires connection to other ICs. You have to incorporate more number of ICs to complete the performance over there, and occupies more spaces and high power consumption. But when you are integrating all this component into that of a single IC chip, that is nothing but a system on chip, it integrates multiple functions under one roof, under one single IC chip. It includes multiple processors. It works independently. It occupies less space than that of your application specific ICs over there. So ICs, a chip containing electronic components for a particular specific applications. However, SoC, a chip with a complete system built inside. It is the system itself. That is why we call them as a system on chip. So all SoCs are ICs, but not all ICs are SoCs. So you need a n number of IC modules in order to make it as an one single SoCs over there. So some of the examples, 555 timer and 7400 NAND gates are the ICs over there, and STM 32 Raspberry Pi Pico or SoCs over there. So why we need these SoCs? Why we are moving from that of an application specific to that of an system on chip? The one straightforward answer is the miniature. We need a minimum size, minimum area in your gadgets or any electronic systems with a maximum performance. So we are moving from the PCB, which incorporating n number of modules into that of a single SoC. So we are just reducing the size, we are reducing the area, and by we are reducing the power consumption, and we are increasing the speed, the performance of the any type of an electronic system gadgets what we are using over there. So what is the SoC definition, system on chip definition, when we are looking forward? So in with respect to the top and VLSI manufacturing, technology advances has made possible to put millions of transistors on a single die. It enables designers to put system on chip that move everything from one board into the chip eventually. This is the one definition. When you ask to the another person, it might say SoC is a high performance microprocessor, since we can program and give instructions to the microprocessor to do whatever we want to do. It is nothing but the controlling unit in order to align the controlment over there. But there is another definition also. So SoC is the efforts to integrate heterogeneous or different types of silicon IPs on the same chip, like a memory unit, microprocessor, random logics, and analog circuitry. So are these are the only definitions? No, we do have. So all of these above definitions are partially right, but not very accurate. So when we want to talk about an SoC, what is an SoC? SoC itself a system. Its SoC has an everything on it. It is a system with that of a chip, with that of a software, with that of an hardware in that. So the SoC chip, it includes the embedded processor, the entire processor, the controlling unit. It has some ASIC logics, and it has some analog circuitry for communications. It has some embedded memory also. So it has a two component, the hardware component and the software component. So the SoC software, it includes a OS model, compiler, simulator, firmware, driver, protocol, stack integrated development environment like a debugger, a linker, loader, IC, and the application interface like an assembly part also. However, the SoC integration, it includes a whole system solution, manufacturing consultant, and a technical support over there. So what is now SoC? The SoC is itself an hardware. The SoC itself and software. The SoC, it includes a CPU, it includes a GPU, it has a DSP, digital signal processing unit, it has a networking unit, it has a memory unit, it has an input output interface over there. SoC, it's a build of everything over there. So what is the major applications of SoC? Why we need a secured SoC? That's what we are going to discuss today. So the application of SOC, everywhere we are using the SOC in order to have a controlled manner, in order to have an IoT applications, in order to have an automations, in order to have an straightforward data communications like wireless communications, information technology. We have a PC interface. Now everything is a smartness. The smartness with respect to smart city, smart home, smart university, smart parking system, smart car, everything is smart over here. So n number of applications can be built with the help of this SOC over there. So now we are diving from the top and understanding of what is SOC to what are the real challenges, particularly with respect to the top of security aspects when you are designing the SOC at the hardware level. So the real time challenges with respect to SOC is you have to build the entire system with n number of modules inside a single IC chip. It's going to be the nightmare challenge over there. So the design is going to be the complex. Think about this. If you have a 10 transistor design inside the transistor, inside those who have taped out the IC chips, you might have a better idea about that. If you are taping out a IC chip which has 100 transistor, it is going to be a complex. If you are taping out the IC chip, if it has 1,000 transistor, it is going to be a bit more challenge over there. Now the SOCs are with a millions of transistors, close to that of a billions of transistors. So the designs are complex inside that, and we need to use a structured design technique and sophisticated design tools to manage the complexity of the design. And we have a multi-layer IC design, chip design nowadays. So how to place those transistor, at which layer we have to place, and how to module, how to communicate between the transistor, which transistor has to be placed next to the other. Everything matters here. So you are increasing the design complexity, which is going to be increasing the challenges to the design engineers as well as the verification engineers. We also accept the fact that our any technology we learn the details of to be out of date soon. So I started my BTech project with 180 nanometer technology. Currently 2 nanometer, my students are practicing with a 2 nanometer, 5 nanometer technology. So the technology advancement we have to update. So as a faculty, as a student, adopting the technology itself a challenge. Think about the semiconductor manufacturing industry adopting that technology in order to have their betterment. Time to market challenges are there. So these SOCs are giving highly challenges for these design engineers and verification engineers. So as a chip design complexity increases, so do the challenges of ensuring the functionality. Yes, we are incorporating billions of transistors inside the IC chip of an SOC, but we are not going to compromise on its functionality. We need a high performance with a minimum power consumption, with a minimum area, high reliability, and manufacturability of the chip. That is what we are expecting from any gadgets. So if you want to buy any electronic systems, what we are looking for, what is the processor in the system? That is what our first question is. That an Apple processor or an Intel processor or it is an AMD processor we are looking for? Do you have a GPU? Is that an NVIDIA GPU or any other GPU? That's what our first preference will be. So we need a high performance. Then verification and security validation, how secured our system is. Nowadays all our passwords are linked with our mobile phone, all our pass keys are linked with our mobile phone. If your mobile phone is threatened, definitely everything you will lose over there. So we need a security over there. How to verify all these components, all these design components, everything is a real challenge over there. So the product security is different from that of an application security. The product is an end product when it comes into the application. So if I'm using my smart system, if I'm automating my house, I'm connecting everything with my laptop or my gadget. If that laptop is vulnerable, definitely the entire house is vulnerable. The entire automated house is going to be vulnerable. Anyone can threat the house. Anyone can open my smart lock door system over there. So when it comes into the security, we have to concern about the product security, the end product security, and also about the application spec security. Since these SOCs are the heart of an any digital systems. They are the controlling part. If your SoC is vulnerable to any hardware threats or any vulnerability, the entire system which is built on the top of this SoC in any application for any application is going to be threatened. Now you realize the real challenges with respect to that of an SoC as a design engineer and as the security perspective over there. So in today's lecture, we are going to touch up with the of a security validation with respect to the of an SoC. Now comes into the essence of this particular session, that is an hardware vulnerabilities in SoC. So what are the hardware vulnerabilities in the SoCs we are looking for? The SoC, the heart of the chip, yes, we are convinced that, and we need SoC for integrating n number of modules. Yes, we are convinced with that. Now comes the real picture, how the hardware vulnerabilities in the SoCs. So any type of an hacker, it might be the software hacker or it might be the hardware hacker, can easily hack your central processing unit which is built with it of an SoC over there. So that is the major hardware vulnerability. The vulnerability or the threat, it might be the hardware level or the software level. If your SoC is vulnerable to any type of an attack or any type of an threat over there, definitely there is a huge chance for the attacker or adversary to crack your system over there. So with that, now we are in the smart world. Everything is connected under the one cloud roof over there. The internet is connecting everything. If your system, if any one of the system is vulnerable, the attacker can easily attack any module or any system connected to that particular application over there. So that is where we are right now. So the hardware vulnerability in SoC are very, very vulnerable and they are challenging for the security engineers over there. So with this as a background, now let us deep dive into what is the hardware security, why we need a hardware security. The hardware, what I'm referring right now from right now is going to be the IC chip, and the IC chip is nothing but your SoC itself an IC chip, right? So the cyber security experts have traditionally assumed that the hardware underlying information system is secure and trusted. So everywhere you need a cyber security experts in order to make sure that your system is not vulnerable, that your system is trustworthy, that your system is secured in nature. However, such assumption is no longer true. So that you can't say that once you are at the end user side, anything can happen. As an end user, you might give the back door for the software people to access your hardware. So simply if you download any particular applications, the application definitely it will access your entire photos. I don't know why any application what we are downloading to our hardware need access to our privacy picture storage, photos, images, and any contact details. What is the requirement for their access for the contact details? So the software which we are downloading for our hardware might be vulnerable. So we are no longer assuming that our software is going to be a trustworthy and our hardware is going to be a trustworthy. So if you go to the public mall or a public place, there if you're connecting to the Wi-Fi over there, is that a secure? As a security engineer, I won't say it's not. It's not a trusty thing to do. So that's what we are going to. Anywhere, everywhere, if you are using anything which is behind your control, which is not trustworthy, it is going to create some kind of security issues or challenges. They might access your contacts, they might access your photos, they might access your private contacts in your any type of gadgets over there. So the hardware security and the software security, it depends on the IC chip security over there. So at this point, do you think this is a need for an hour? Do we need a hardware security or not? At least we need some awareness about a hardware security. I really appreciate for having this session to have just a hardware security awareness. This is the awareness I just want you guys to know how vulnerable our software is, how vulnerable our hardware, what we are using in our day-to-day life. So what is the hardware? The hardware is nothing but IC chip. It might be the microprocessor or it might be the SoC. So SoC, system on chip, is embedded in any type of an gadgets or an application specific printed circuit board, though or the heart of your system. Okay, so the root of trust has to be built at the heart of your system. The heart of a system is nothing but your IC chip or an SoC over there. It might be the microprocessor or it might be the system on chip. So we are going to study, we are going to learn about what are the vulnerabilities at the root of the system, what we are using in our daily life. So with this, any questions in the chat box? Let me take a water break. So I didn't see any questions in the chat box. So moving forward, so hardware, what we are referring from right now is an IC chip, SoC or field programmable gate array and the entire embedded system. And the security, what we are going to discuss is the vulnerabilities, threats, attack from the hardware side, which is going to be the backdoor for the software in order to perform any software attack over there. And we are going to talk about an hardware design security and hardware for security also. So need for hardware security, yes. I believe with these slides for 30 minutes of discussion, we have come to a point we need a hardware security. That is, an hardware is a root of trust. Even a small malicious modification or a small malicious Trojan circuits can be devastating to the system security. So yes, we need a hardware security awareness at least. So what is required in any hardware or any SoC? The trust is required. You need a trusted platform. So that is what lagging in today's world, real-time world, we are lagging the trust. So what is missing? Our hardware, our gadgets, what we are using in our day-to-day life is nothing but seeking our privacy. It is always monitoring our privacy data. Yes, Google knows they are collecting the data, and what they know where I am, what I'm doing right now, and do I'm going for a walk or do I'm driving the car, do I'm going for the shopping, do I want to shop any particular item. Everything is known. They are collecting our data. So we are losing our privacy. That is what we are missing. And what are the backdoor for that? Our hardwares are the backdoor for that. So someone is monitoring us and we are losing our privacy and we are losing our trust on our hardware, I believe. So what is the motivation over there? So the hardware security is becoming increasingly important with respect to the toughened system on chip or any application specific ICs. The hardware security sneaks into PCs. Robert Lams reported that in 2005 itself. And in 2005, Microsoft reveals a hardware security plan. And the Princeton professor finds no hardware is secured in e-voting machine. Okay, that is what reported in Information Week. In 2007, secure chips for gadgets set to soar. Yes, it's true. We are not going to trust our gadgets anymore. So in 2006, they have reported Army requires security hardware for all PCs. So is it the same kind of SoCs we are going to use in our laptops is going to be used for the defense system? No, the defense systems needs a high, secure, trustworthy IC chips. Okay, so if you are more interested in the hardware security, kindly follow us in a Facebook group of hardware security, which is maintained, developed, and maintained by my mentor, Dr. Mark Takaranipur, and his team in University of Florida. So hardware security is not developed yesterday or today. So you can see in 1996, the hardware security is paved out over there. And it is an evolution from 2002. There comes the physical unclonable function to random number generator for a hardware tagging. And 2004 to 2007, DARPA trust, the hardware trust has started. US has started spending more money in billions of dollars in building a trustworthy hardwares over there. And in 2016, you can find a design for trust techniques are developed like logic locking, split manufacturing, and IC camouflaging and Trojan activation. And 2019, trustable hardware with embedded security primitives are developed. And right now, we are with an AI module. In 2025, we have an AI-oriented hardware security features in order to increase the build trust with respect to the top and any IC chip over there. These are some of the reported issues with respect to hardware security from 2019 and earlier days. Over a decade, when I'm defending my thesis, I used to get comments from my peer group and my friends and colleagues that, oh ma'am, you are just uh, you are just introducing some hardware vulnerability by yourself called as hardware trojan, then you are detecting that. Then I want to give them the proof of record. These are the proof of record reported issues, that this is not a simple problem. This is the universal problem. This is an every individual problem, what we are facing with our hardware. Since each individual, we are connected with n number of gadgets, and we are connected with n number of applications of an IoT application. So the hardware security is not meant only for the government, it is meant for then each individual over there. So in 2019, Cincinnati, that is the University of Cincinnati, they have reported that regardless of how secure you make your software, if your hardware leaks information, you can basically bypass all those security mechanisms. Yes, there are a lot of malfunctions with respect to software. You have security features over there, but everything can be broken down into pieces if your hardware is vulnerable over there. Then in 2000, I think in 2018, there is an another report issued in the conversation journal. It means that don't trust your hardware, why security vulnerabilities affect all of us. And the another reported issues studies with respect to microchips is like an hacked hardware could cause the next big security breach. And there are some of lot of hardware attacks reported in our day-to-day life, and I want to give you some glimpse of that. So in 2009, that there is a reported attack, that is a trojan kill switches in military technologies. So it is reported in New York Times in this week. Since section the hardware and software trojan kill switches, that is what they have
ശനിയാഴ്ചയാണോ പോകുന്നത്? ശനിയാഴ്ച തന്നെ പോണോ?
okay.
ആ
So there are other example attacks also, like fake Cisco routers and energy theft going from bad to worse. So the energy, the power system, the smart grids, which are supplying an oil, electricity, and gases, they are vulnerable since with that of an hardware attacks over there, and 1 billion loss in CT because of an electricity theft. This is a huge over there at the time. And fake Cisco routers, the routers which are connecting n number of systems into the top one network, they are fake in nature. And IT subversion have been dropped over a $76 million because of these fake Cisco routers over there. So the other example attacks. So now we are implanting electronics, any systems into the top of your human body, like an implantable cardio ventilator, defibrillator. These are in order to monitor your heart, those who have a weak heart systems over there. So these medical devices are highly risky. Anyone, the pacemaker attack is very popular over there. I'm sorry. The pacemaker attack is very popular over there, right? So you might see incorporating security in sometimes considered very expensive with respect to the top and medical device security. Implantable devices, heart rate monitors, some kind of an a monitoring systems is essential for some patients in order to monitor their heart beating and in order to support for their heart health over there. And if those medical devices are vulnerable, definitely the human life will be in danger, will be questionable over there. So attacking these devices could result in loss of life. So this is since it's a loss of life, when it comes into the life, we will give some kind of attention, more attention over there. So there are some articles with respect to the top of vulnerable medical devices, implantable vulnerable medical devices with respect to security issues. If you are more interested, I recommend you guys to deep dive into that. Then other attacks like physical attacks on chip IDs, that extracting secret keys, that is a very popular attack nowadays. The money is theft over there without our knowledge from our ATM card and bank account. Those are nothing but physical attacks over there. Then we have a side channel attacks like a power analysis attack, time analysis attack, and electromagnetic radiation attacks. And these require some kind of setups like this. They need an oscilloscope, they need a signal generator, and they need a one particular side channel analysis part in order to perform the attack. And tampering with electronic devices and capture drone by Iran is one popular attack during an Iran-Iraq war over there. Then counterfeiting integrated circuits, multi-billion dollar business is running. So there will be a fake ICs in the market. We don't know what is the fake IC and what is the real IC, what is the original IC. So you might have experienced that the same product you might have get here at a lesser price in your black market. How it possible? Those are nothing but counterfeit IC. The product is not real, the product is not original. You might, for example, iPhone, you might have got for a cheaper price. Do you think they are the original iPhones? Not exactly. They are the counterfeit ICs. It is vulnerable to any type of an attack. It might burst also. So you might be aware when you are investing your money in those cheaper items in your black markets over there. The smart card attack is very popular over there. By the end of 2006, Western European countries fully migrated towards the smart card. That's like an voting, telecommunication, mass transit. And this smart card attack has caused $1 billion loss with respect to the top and hardware attack over there. So this is the architecture for a smart card attack. The smart card attack is possible either the victim is closer to the system or remotely also. And you can see the victim card is reached by the attacker through his NFC equipment mobile phone connected to an NFC equipment mobile phone in the proxy of the card. So if you are accessing your smart card in your ATM machine, those who are standing next to you can access your PIN number, can steal your PIN number, can threaten your PIN number from your ATM machine. That is possible. That is the well-known attack with respect to the Toffen smart card attack architecture. And the phone close to the victim card can be instructed to the run local attacks. So n number of attacks, they can steal the contact details over there. So these type of smart card attacks are very popular in our day-to-day life. If you are more interested in a smart card attacks, you can just go through these articles and you can educate yourself how these smart card attacks are happening in our day-to-day life, reality life over there. So a smart card attack, some examples, we have a relay attack against a contactless smart card. That's what we have seen. With the help of a proxy mobile phone, you can extract the data from the victim. And there is a remote attack or contactless attack also. So the people who are outside the ATM, I'm giving the example of an ATM machine for a better understanding. That is not the right scenario anytime. So the people who are standing out of the remote ATM machine can also extract your information by means of reading the communication from your card, wireless card over that. So this is another smart card attack example. RFIDs or radio frequency identification is the use of an object applied to or incorporated into the product, animal, or person for the purpose of identification and tracking using a radio waves. Of these IDs can be used as a tracking mechanism for any items in your shop for shoplifting or for your animals in order to monitor the animals. And even in US, recently we went for a Thanksgiving party, and one of my friend is very cool, and I'm asking, hey, you're not checking with your kid? How come? Hey, I'm just checking with my mobile phone. She's having an air tag in her shoe, so I'm just checking her through monitoring her in my mobile phone. So every 10 minutes she's checking her mobile phone. She's checking not her daughter, she's checking on a mobile phone. So what is that? That is nothing but your ID, RFIDs. Air tags are nothing but your RFIDs. So that is an advantage of having those IDs, but in the other perspective, that can be a threat and is also possible. So most RFIDs contain at least two parts: an integrated circuit for a radio frequency and an antenna for receiving and transmitting the signal. So some are active by battery and some by the passive over there. So what kind of attacks? There are n type of an applications in securing a transaction with RFIDs, like an inventory control container, pallet tracking for a car parking, and ID badges and access control, maintenance equipment, and personal tracking in hospitals, and parking lot access and control. That is a very good advantage with RFID. So which slot is open? Either I have to park in this particular parking location. Do I have a space to park my car, or I have to go for another parking before reaching the destination? I can able to identify my parking lot over there. That is a car tracking in rental lots. And the product tracking through manufacturing and assembly, even shopliftings they will be using. And in order to avoid a shoplifting, they will be using RFIDs. So what is the challenge? Yeah, we have an n number of applications. Our life is ease over there. Can we create security mechanism light enough to be suitable for the RFIDs? That is the challenge. So what is in your mind now? I want to read your mind, guys, after listening to a 50 minutes of this session. Do you guys think are we on a trusted platform with all these ease making things with our gadgets? For me, absolutely no. The answer is no. I'm losing something. I'm losing my privacy. I'm losing my individuality. I'm losing what I'm thinking is known to the Google always. Before I'm thinking, I'm getting the answer from the Google. Is this the right thing? Is it the peaceful thing I'm looking for as a hardware security engineer for more than a decade? No, my answer is no. I'm losing something over there. So the vulnerabilities and threats in hardware and countermeasure against the hardware threats and security evaluation is required on how to design a secured IC or a secured SoC is what in my mind right now as a motivation of these kind of threats and challenges in an SoC chip design. So with this, let us deep dive into what are the hardware security threats in our day-to-day life with respect to the tough and gadgets or any type of applications what we are using, and how anyone, either the software attack or a hardware attack is possible with respect to the top this hardware security threats and vulnerabilities. So hardware design flow, how the IC chips are designed. That from there itself, the hardware is vulnerable. So we have to know how the IC chip is designed. I'm just not going to deep dive on that. Just I have to glimpse your idea about an hardware design flow and what are the trust issues with the IC supply chain. What are the attacks and what are the countermeasures with respect to the tough and SoC chip. So any electronic hardware flow, it might be the IC application specific IC or a system on chip. This is the high level overview. You have an intellectual property vendor where you will be collecting IC specifications, and the design house will be there. They will be converting the specification, the functional specification and the design specification into that of an IC, that is an RTL module. The end product will be the GDS2 file, that is the layout file, and that layout file, the output or the end product of your IC design house will be given to the manufacturing unit or the fabrication part where they will manufacture the IC chip. It might be the application specific IC, or it might be a processor, or it might be the SoC level over there. Then those IC chips are manufactured, and they will be sealed or covered, and they will be given to the end user. They will be embedded in any PCB for the any type of an applications of an embedded system. Then they will be given to the end users. So these are the four scenarios of an high level hardware design module from the design perspective of an IP vendor with specification, with an design specification and functional specification, and to the top an end product. So where we are now at the IP vendor itself vulnerable. Some 5 years or 10 years back, I believe, there is a reported issue that Dell laptops are vulnerable. They are purposefully creating some kind of malfunction. We call them as a denial of service. So after a certain usage, that particular laptop will give you degrade in the performance. So obviously we have to change the gadget or the laptop or whatever it may be, we are used to that particular model, that particular company, that particular vendor. So we will be upgrading our system with the same vendor itself. So that is a one big threat at the IP level. Then at the design house itself, yes, design house, there are a lot of reported issues. There are a lot of possibility in order to make your hardware design vulnerable without the knowledge of the IP vendor itself. At the manufacturing unit, yes, obviously, yes, some of the manufacturing defects may also be reported as the hardware vulnerability over there. So yes, obviously, at the end user side, threats like counterfeiting and recycling the ICs are possible at the end user size. So at each stages of an hardware design flow, or at each stages of an IC design flow, or at the each stage of an SoC design flow, the hardware is vulnerable to any type of an attack. So that is the real truth we have to accept in our day-to-day life. So with this, I have a small video for you to understand the manufacturing of an IC. Even during rush hour. Try loop earplugs now. Sorry. Whether you want to shut off while commuting or still. Thank you. So I just want you guys to have an high level idea of how ICs are manufactured. So I believe this short video will give you a better understanding of how ICs are manufactured. So now we are with an major security issues in an IC design flow. So as I told you, we have break down the IC life cycle or the IC design into four major components. One is an IP vendor, where your specifications are developed with respect to the functional requirement and the design requirement. And with respect to that, the SoC design house will create a RTL, that is a GDS2 file, in order to meet a functional specification and the design specification. Once they develop that layout, that GDS2 file, they will be given to the foundry, and foundry will develop or manufacture the IC. That's what the glimpse of video what you have seen right now. And once the ICs are manufactured, they are packed and they are deployed for a end user, like an embedded systems applications over there. So what are the hardware threats related to these kind of an IC design flow? At an IP vendor, they are purposefully insert some hardware trojans, and they will cause some hidden backdoor attack, like an either the hardware attack or a software attack is possible with the help of these hardware trojans. So with respect to the of an SoC design house, you might have an IP piracy. That is, we will deep down into what are these threats. And at SoC design house, again, a Trojan insertion is possible. And at the foundry, at the manufacturing unit, again, implanting a Trojan is possible. And IC overproduction and cloning is also possible. And leakage of secret information and the reverse engineering and cloning are the hardware threats with respect to that of a deployment at that of an embedded system level. So this is how these threats are related to that of an major IC design flow steps. So why these threats occurs? How it possible? The only reason is all of the four major steps in the IC design flow, what we have discussed is not under a one single roof. They are distributed globally. So any one at any stages of an IC design flow, they have an access to this particular IC, and they may add any type of an vulnerability or threats over there. I always say my students when I am teaching this course, I always say, if you are having some fight with your sibling and you miss to take your tiffin box to your lunch box and to your school, and if a mom is sending lunch with your sibling, the sibling may add any type of an extra things like an salt or water or sugar to your lunchbox in order to threaten you. So likewise, the IC life cycle also the same way. If the vulnerable, the adversaries are at any stages of an IC design flow and they have a chance to add any type of vulnerability, either purposefully, either intentionally or unintentionally, they can do that over there. So the only reason is outsourcing the fabrication and the design to the third parties imputed to the huge scales of requirements and economics involved. We don't have a one single roof for our IC manufacturing. That's why. So outsourcing the chip design process, how it possible? The product design will be happening at one place. For example, let us assume it is happening at the United States. However, we don't have a fabrication unit with a recent technology. We have to upgrade the technology. Right now, we are with a 5 nanometer technology. So the Taiwan manufacturing unit is the only place where you will be having a upgraded technology over there. So obviously we have to outsource for our fabricate manufacturing process to Taiwan. So once the Taiwan is done with an IC manufacturing, it will ship the ICs to that of an another unit. It might be the China where your components are integrated into that of an PCB board. Then the final assembly will be done in Philippines or a Korea or a Japan. So throughout globally, the entire IC chip design process is distributed. That's why we are lagging our trust on our IC chips over there. Okay. So what are the hardware threats, possible hardware threats with respect to the of an SoC design vulnerabilities? They are IP piracy, IC counterfeiting, hardware backdoors and Trojan horses, IC tampering, IC reverse engineering, IC recycling process, and physical attacks. So these are the listed hardware threat vulnerabilities. Now AI plays a major role. So now AI make the attacker point perspective very easy. AI is helping all our adversaries in order to make their adversarial activities more easy than that of an previous era. So what is IP piracy? The IP piracy is nothing but stealing the IP without the owner's approval. So if Alice is the selling his IC, he is giving the IP to that of your Bob by in terms of trusty worthy. But Bob, he is a vulnerable and he's an adversary. He is stealing Alice's IP and reselling to Charles, either to that of an less cost or in order to enhance his business. So the stealing IP without a owner's approval is very common. Why? The IPs, the intellectual property, plays the major role. The idea is much more important than that of an end product. The IP, intellectual property, it has both a functional specification and the design specification. So the end product, it depends on this functional essence over there. So the IP piracy is an highly vulnerable threat. Excuse. My excuse. So it is highly profitable in market. Then comes the IC piracy. As like that of an IP piracy, the IC design house, they might overproduce, they might steal this IP and they will sell it to the other vendors also. And the IC design house, they are converting the function specification with respect to that of a design specification into that of a layout. And there are a lot of verification terminologies with respect to that of your end product GDS2 file. The manufacturing unit, without the knowledge of an IC design house, what they will do, they will manufacture pirated ICs. They will overproduce those ICs and with unauthorized production and sell it in the black market. For example, if I'm the IC design house and I want to design a microprocessor, RISC-V microprocessor, and I'm giving my design with my GDS2 file to the manufacturing unit, fabrication unit, and the person or the adversary in the fabrication unit, they felt this is the best RISC-V processor with a very good specification with respect to the of a design specification and the functional specification. So the manufacturing unit, they will reach out to another vendor. Okay. So other vendor is ready to take that IP over there, IC over there, and they will manufacture the additional IC without the permission of myself, and they will sell in the black market over there. Okay. So this is an highly rated threat uh, in a IC manufacturing side. Then counterfeiting, IC counterfeiting is another, sorry. Everyone's heard of speed dating. I have another. But what if I told you there's now speed funding for businesses where lenders actually. So this is how the IC counterfeiting will be used. You might have seen it's most popular in electronic um, shops in US. So what they will do is they will collect the used laptops or anything and they will reuse those ICs. Okay, this is much more popular. I think in even in India they are collecting some unused used and faulty gadgets and they will counterfeit the ICs over there. So this is the most prevalent attack today. So unauthorized production of waivers, it is estimated that counterfeiting is costing semiconductor industry more than the $7 billion. You cannot able to say which is the fake IC and which is the original IC over there. You can see both the ICs are have labeled as an Intel, but you may not say which one is fake, which is the counterfeit IC or which is the real IC over there. This is the most common attack right now. Okay, so from the used products, they are collecting the ICs and they are making the other products with these ICs. Hardware backdoor attacks. A component of the device is altered in some way. Okay, this include a computer chips, hard drives, CPUs, and other elements. And this method provides attackers with root level access to the devices and the system. So the hardware, some vulnerability in the hardware is going to lean towards a software attack. So the non-computer hardware can also be used for this way. So the non-computer hardware, other than the ICs, there are some other components also. They can also leak the informations. And by analyzing a side channel analysis, anyone can attack the hardware or anyone can make a backdoor attack on the software also. So these includes the cell phones, home security systems, thermostats, and other devices. So when this happens, attackers can gain access to the device, to its systems and the data that is found within. The most popular attack in US is a Wi-Fi attack. So not all the houses are paying for their Wi-Fi. Some will be theft. Wi-Fi theft is most common with some routers over there. So they are saving some $100 a month. That's a huge amount when comes into that of an 12 months package over there. So these hardware backdoor attack are commons in with our daily usage of our hardwares. So the hardware backdoor is usually used for surveillance capabilities and or to gain a remote access over there. And one popular funny attack is like an surveillance camera. One of the reported attack is the surveillance camera is not surveilling the house it is fitted, it is surveilling the neighbor house. So the neighbor person has made some attack over there, and he made that surveillance camera to capture his house image rather than capturing the owner's house over there. So this is looks like a funny, but these attacks are more popular over there. So the other most popular attack and very close to me, what I have worked for more than a decade, is a Trojan horse. So these Trojans are nothing but malicious modifications done in the design itself. At the IP level, at the design level, we are injecting some kind of, we are populating some kind of malicious circuits to that of an original design by, and these trojans are inserted in such a way that the adversary is much more intelligent than that of an defender, so they are very extremely small in size, so area overhead is not reported, and their nature is to remain stealthy until they are detected, until they are triggered. They will remain quite stealthy, they have no effect, they don't create any malfunctions, they are very quiet nature over there, and it causes IC to malfunction in the field. So whenever your ICs are in the field, they will cause the malfunction. The attack might be like a leakage of sensitive information, which is much more popular, like your RFID, smart card ID theft, or modify the functionality, that is a denial of service is possible, and reduce the reliability of your system. That is what your these Trojan horses are popular. Even the defense systems, they have this Trojan horse reported attack in our Syrian war with between Iran and Iraq. This is Trojan attack is much more popular over there. Then comes the IC tampering. IC tampering is a much more popular attack. So it is nothing but a reverse engineering of the IC. So why I am giving you these kind of videos? So this is for your better understanding. So the IC tampering is removing the IC layer by layer so that you can able to extract the layout of your IC. You can extract the transistor level details of your IC. So that is how the manufacturing unit are making a packaging more difficult with some kind of an ultra which are like a layer, providing some chemical layers in order to avoid these IC tampering over there. But these attacks are much more popular by means of putting some laser beam. You are tampering the IC layer by layer, and you are capturing the essence, the layout over there. So this is the most popular attack. So I'm bringing all these videos in order to give you some visual concept. These are the real attacks in our day-to-day life so that you will have a better understanding over there. So IC reverse engineering is an very popular attack. So anyone can reverse engineer the IC counterfeiting we have seen, collecting the ICs, the used ICs, and you can reverse engineer by IC tampering. Then you can reach out to the netlist. This is like that of an bottom to top approach in order to attain your design level specification. What is your design over there by means of a reverse engineering over. So IC recycling, the old ICs are recycled and used without our knowledge. You might have seen some kind of denial of service is possible with the performance of your IC. With the hell, these are nothing but the old IC. The aging of ICs, it will cause some denial of service over there. So these old ICs are engraved in your embedded system. They might cause denial of service. They will degrade the performance. They will degrade the reliability of your electronic gadgets over there. Okay. So there are a lot of reports. Some people used to say that silicon in the IC you can extract a gold. So that is also the IC recycling. People will collect the old ICs and they're trying to extract gold. That's a funny thing, but these are really reported issues over there. So the physical attack, which is the most popular attack, that is a side channel attack. You need some additional equipment like your oscilloscope, some preferred probes. So the side channel information like power consumption, electromagnetic radiation, injection of faults, and sounds are also possible. When your logics moving from 0 to 1 and 1 to 0 at your hardware level, these side channel analysis will help you to gather the information of its performance over there. So any queries as of now? Let me check the chat box. Okay, I'm just want to ask you, do we need a hardware security or not? We are prone to these type of vulnerabilities in our day-to-day life. Yes, the answer is yes. Now let us have a quick, what are the countermeasure against these before winding up this session? So the measure against these hardware attacks. So again, we have a breakdown the entire IC life cycle, that is an SoC life cycle, into four major types: IP vendor, SoC level, design level, foundry level, and at a deployment level at the end user level, and their corresponding attacks like an hardware Trojan backdoor, IP piracy, IC piracy, Trojan insertion, overproduction, IC cloning, side channel attacks, reverse engineering, scan-based attacks, and IC counterfeiting. So what are the countermeasures? So in order to protect your hardware from the top and hardware Trojan attack, you have to build your IP, intellectual property trust verification. The hardware IP trust verification is a functional verification, is a design verification techniques. You have to adopt those verification as a countermeasures in order to make sure that your IC is a Trojan free or not. Then IP, in order to protect your IP from an IP piracy, you need an watermarking. So watermarking is a process where you are going to engrave your signature to make sure that this IP is belong to this particular owner. This IP's owner is this, so that no one can take ownership of your IP. Then comes a hardware obfuscation or a hardware logic locking technique. So you are going to lock the logical functionality of your design, so that anyone who's having the access at any stages of your IC life cycle may not able to incorporate any type of a malfunction or any type of an any type of an vulnerability over that. That is an hardware obfuscation, is a popular countermeasure for any hardware vulnerability. Then at a foundry level, you can detect the Trojan by means of a Trojan detection techniques. There are a lot of Trojan detection techniques. Even the side channel analysis, you can make a Trojan detection techniques, and a lot of ATPG techniques are also there in order to detect the Trojan. And hardware authentication, you are giving some kind of additional assurance by means of an online monitoring systems, by means of an continuous monitoring systems, real-time monitoring systems, real-time monitoring approaches, so that you are every time you are authenticating that this IC is free from your any type of an hardware vulnerability. Every time you are testing with respect to security aspect. However, the testing or verification with respect to security aspect has to be done parallelly to that of a normal verification functional specification over there. Then comes a side channel resistant design. So as I told you, the ICs, when you are packaging the ICs, some special kind of chemicals will be covered on the IC packaging, so that any type of a side channel attack is resistant to those ICs which are covered by those chemical over there, so that extracting the data by means of a side channel analysis is avoided over there. Then secure scan design, that is a popular countermeasure in order to in order to protect from a scan based attacks over there. So these are the popular countermeasures in order against the hardware attacks in our day to day life. It might be the IC or it might be the SoC over there. So why we need a secured SoC? We need a secured SoC since SoC, the system on chips, are highly used for n number of applications, particularly in an automations applications, particularly in a remote control applications. We need these SoC chip in order to automate the process, in order to segregate the process, in order to sequence the process one by one. So the software is not enough to fully protect the system. We need a hardware. If there is any backdoor in the hardware, it is possible to perform a hardware attack and as well as a software attack also. So the security in hardware offers a performance and power consumption advantages over its software equivalents. So whatever the software you are running on the top of the hardware, it should be vulnerable. It should not be vulnerable to any type of an attack. So what is the assurance? The assurance should be given at the hardware level. So increasing amounts of data being processed and the complexity of encryption algorithms slows down security implementations severely. So oftentimes these same encryption algorithms can be implemented in the hardware with respect to that of a software. That comes the hardware software co-design. So now we are talking about a hardware software co-design. So the secured SoC will help us to build n number of applications in the trustworthy manner. So we need a hardware security, we need a software security, we need a hardware software co-design security in order to build a healthy community. So these are some interesting articles you can go through if you are more interested in these topics. And I have some datas how this global microelectronics market size and what is the forecasting for 2030 and billions of dollars like a 455.67 billions of dollars are going to be invested in this microelectronics market. And even India is investing a lot of projects in the semiconductor industry. So global semiconductor market forecast in 2026 is a huge 75% more than that of a growth right now what we have. And leading edge technologies, we are with the 2 nanometer technology right now, and maybe we will be end up with some other new technology in the upcoming days, we believe. So as a summary, we have a lot of security challenges with respect to SoC, since with respect it has a design complexity over there, and we have a high level overview of what are the hardware vulnerabilities and threats with respect to SoC and need for hardware security, since these SoCs are incorporated in n number of applications from IoT applications and automation applications, and there are supply chain vulnerabilities at each stages of an IC design flow from IP vendor to that of an deployment end product. We have seen their countermeasures also. So that's all. I believe I have covered this section. I have given met your expectations. If you have any questions, let me know. I want to acknowledge some of the datas presented here, or I have the resources from the hardware security research community and some of the conference publications and journals. And I'm acknowledging everyone who are helpful in order to make this presentation. So with this, any question, I'm open to take any questions. And thank you all for patiently listening to this session. I believe I have given you the high level overview of what are the security challenges and countermeasures with respect to SoC design and why it is need for an hour. And as an electronic system users, as an end users, we have to be aware of all these security challenges what we are facing. So you can reach out to me in my LinkedIn. I'm a active member in LinkedIn. I will happy to answer your queries and happy to work. Looking forward to work with you in near future. Open to collaborate also, collaborative work also. So any feedback is acceptable, and happy to receive the feedback, take the feedback, and it will help me to improvise myself.
Uh,
Thank you, Dr. Nalish and team, for giving me this opportunity. I can take the questions right now. Thank you.
Yeah.
Good evening, madam.
Yes, please.
Yeah, madam, once the GDS file is handed over to the foundry from the a particular customer, whose responsibility is to ensure that it is being saved or secured in an appropriate manner, ma'am? Whether the customer have a say or the complete responsibility of the foundry to ensure that it is being protected? Or
That's a very
in which sense the customer can ensure that everything is being protected?
that's a very good question. So I really appreciate that. But the answer is no. No one is responsible. That is the big challenge we have here. So everyone has to trust the process, and we are not going to trust the design end product over there. That is the hard truth we have to accept. That's why we always name this as a cat and mouse game. So if you are ensuring any particular threat is not there in that particular design, that might be a backdoor for the any other threat over there. For example, if I'm making ensuring that this particular design is not vulnerable to hardware trojan, yes, I can ensure that. But what about the another threat? Will it be vulnerable to IC counterfeiting or not? I don't have a
True.
control over that.
True.
See, so that is this is always like a cat and mouse game. So I always tell my students, those who are taking this hardware security course, guys, you guys have an evergreen market in this domain, since this is always like an cat and mouse race. It's going to be evergreen. One threat will be there, and if you are developing a countermeasure, definitely the other threat will emerge from that. So it's like an continuous process. But I really appreciate your question. We need some kind of an assurance. That comes the design for security features,
True.
design for trustworthiness. Yes, please.
Madam, the evolvement of AI and machine learning algorithms are how effectively they are being utilized or used in this particular challenge, ma'am. What are the researches going on in this particular problem?
Yeah, exactly. The AI and any LLM models, they are enhancing the security countermeasures. And again, they are also leading the way for the backdoor attack also. So AI is, again, it is playing both the games. And the attacker perspective is also AI is useful in order to build uh, a secure attack. And in the designer perspective also, in order to build the countermeasures, AI is very useful. So it's playing again both the role towards the attacker and towards the defender. And honestly, the AI itself is a challenging when it comes into the security. AI is gathering lot of data and itself is challenging. But when it comes into particular kind of an attack model like an ATPG method, AI is very useful in order to segregate certain type of an test patterns which are more enough to test. So it is reducing the test cost. It is reducing the test time. So time to market, the end product time to market is much more sufficient, much more easier than before with respect to that of an AI verification systems. So AI is very helpful in verification, but comes into the security aspect. AI is also very helpful for the adversary in order to create a new threat model, in order to create an more offended threat model. AI is also
Ah.
useful there also.
And in your complete presentation for about 1.5 hours, and you didn't discuss about any sort of solutions or your suggestions, ma'am. And is there any specific reason for the same?
Yeah, since the threats and the countermeasures are like an emerging day by day, and it's like a rat race, I told you. So the countermeasures, what we have discussed, and the threats, what we have discussed, is a high-level overview of an hardware security. So if you
Right.
want to deep dive, each threat model is a one different uh, topic.
I
Okay.
understand. Yes.
So each threat model, if you want to define, it's like an my 1 decade of research, I have
Sure.
addressed hardware Trojan alone as a threat model. So it is like we need more time to discuss that. So I just gave you the high level overview of what are the threat models and what are the countermeasures built over there. We didn't deep dive into that. If we want to talk about a logical locking, I can talk the entire day. If we want to talk about the design for security, we can talk for a week more than that. So if you are more interested, we can have another session, and we can elaborate that, deep dive into that. It's really interesting topic over there.
And thanks a lot, ma'am. You had given a lot of inputs. And only final query is, I had expected a typical US English from your presentation, but you are speaking a quite very Indian
Since my
discussion.
audience are Indians.
Yeah,
If
ma'am.
I'm taking a class for my students, that will be a difference. Since my audience are Indians, I'm making myself flexible. Thanks for
Oh,
this comment.
thank you, ma'am. Thank you.
Uh, thank you, Dr. Parthasarathy. Any other questions? Yeah, thank you, Dr. Sri Ranjani. As you were answering. So this is only an overview of the various security challenges and the countermeasures. So obviously we cannot go in depth and discuss each of these in a 1.5 hour session. But I think you have given enough pointers for the participants to, if they want to go in depth, there are a lot of resources I'm sure available. With that, I think, is there any other questions to be addressed? Is there any other questions to be addressed? Okay, I think with that we can conclude our session. Once again, really grateful to Dr. Sri Ranjani for accepting our invitation and taking all the effort to share her expertise in this area to our participants. Thank you once again. And I hope we can have such, maybe, as you suggested, more in-depth discussions in this area in the future. Thank you.
Thank you, Dr. Nalish, and thank you for the team and the entire CUSAT